Okay. Well, again, good morning or good afternoon to all of you. Thank you very much for being persistent and keep joining during this week. Today we will keep exploring how to combine uncertainties. But today we will apply approach 2 from IPCC guidelines, that it's the approach that uses Monte Carlo simulation. So I will start sharing my screen, but before starting with today's session, I would like just to answer a few questions that were in the chat from yesterday that I think it's worth going through and spending 5 minutes to go over them. So let me share the screen. Guess you are seeing
Yes, we can see your screen, Diego.
Great, thank you. So there were a few questions regarding the use of the propagation formula approach in the multiplication for cases where we have powers. So in this case that I showed, I applied the equation 3.1 directly to the power as if they were independent variables, which some of you mentioned that they were not independent, and of course they are not. They are fully correlated, so they do not comply with the assumptions, yet we applied it as if they were, as the same we do with most of the cases where uncertainties are large or are not symmetrical or are correlated. We yet can apply approach 1 if that's the only tool we have. So that was the application of this equation when we have power. In reality, since they are not independent variables, we should add, if you remember from where this equation comes from, we ignore some part of the equation that was related to the covariance, the correlation between two variables if they exist. In this case, the correlation exists and it's fully correlated, positively correlated. The correlation coefficient is 1 in this case because it's the same variable. So if we add this part of the equation that we ignore, the assumption that the variables are independent, we will reach to another equation. The same as we apply or derive the equation for the power from the definition. So if we do that, what we will have, we just modified the presentation. We will share the updated version to you to have it with this update. If we want to take into consideration the real formula for power, or if we add the portion that links the two variables that are in reality the same variable, the digestibility, if we do that, we will arrive to a different equation, similar but quite different, in which you could see that the variable, the digestibility, that it's the variable here, let me just use pen, the digestibility, that it's in reality, it's a power, instead of being accounting twice, the effect is that it's accounted 4 times. So this equation keeps the assumption of the original model. Variables are uncorrelated, and it's applicable to multiplications only. If we derive the formula for power, or if for this situation we add that the variables are not independent, we will reach to this formula where the contribution or the effect of the uncertainty of this variable is really 4 times instead of 2 times. Here, this formula gives us 2 times the uncertainty of this variable, but in reality, it should be 4. So the importance is that if you apply the formula, you can apply it directly. But if you want to consider, there are some cases and you want to derive formulas for other cases that are not multiplications or additions, you can do that applying this definition of the linear error propagation technique, and you will reach the correct formula for that function. So that was one of the clarifications that I wanted to add. And that's the same we did with this case, where we have an exponential situation, and we apply the formula and derive the correct propagation formula for linear error propagation approach. The other question I saw in the chat was related to using absolute values, particularly when we have subtractions. So what IPCC tells us is that we have to apply absolute values of the results. You can see here that the modules are on the total emissions. We do not have to apply modules for every single emission source, because in that case, we will not be capturing the real impact of the uncertainty in the result of the inventory. We need here in the denominator the result of the inventory to make it relative, the uncertainty to make it relative to the total inventory values we have. That's why in the case the national GHG inventory in a country is carbon sink, meaning the emissions, the GHG inventory is negative, capturing more than emitting, this value would be negative. So for calculating the relative uncertainty, we'll have to apply the module, the absolute value of the emissions, because we are interested in the magnitude and not if they are positive or negative. But the individual emission sources should be kept with their own symbol, if they are positive or if they are negative. We will see tomorrow the case when we apply the identification of key categories based on uncertainty. And in that case, we will introduce some variation to this case. But for the uncertainty propagation, we have to use the model of the results, not the individual modules for each category. And there was another question related to how to interpret the contribution to variance. The contribution to variance is basically, if you see the formula, you can see that for each category, you need to account for the uncertainty of each category, the emissions for that category. So this gives us the delta in the emissions for that category, and we square that value. So we have this, the variation. We have the variance of that value. And we calculate it relative to the total inventory, the total value of the inventory, also squared to match square in the numerator and the denominator, and this gives us an idea of precisely the contribution, how much the variance of each source contributes to the total emissions. It's an idea of the weight of the uncertainty contribution to each of the category sources. So those were the main questions I identified in the chat yesterday. There were a few other cases related to subtractions, and I see a few now related to what happens when we have similar values and we are in a case like this, where the values we are adding or subtracting are very close one to the other, so the uncertainty increases a lot dramatically. Yes, and that's true, that happened. There's not much we can do about that. That's because of the nature of subtracting two very similar values. As I mentioned yesterday, this is a very studied issue, a numerical problem that it's called catastrophic cancellation, and that happens that the result is maybe fully contaminated with uncertainty. And that's a problem we have to deal with. For those cases, in general, what it's important, we may try to assess the uncertainty of the two variables that are being subtracted instead of the result, because we know the result will be highly uncertain because of the nature of the equation we are using. So we may focus on the uncertainty of the values we are using. Of course, in an extreme case, I see in the chat, if the two variables are exactly the same and the result is 0, in theory, the uncertainty would be infinite. And that's the problem of the catastrophic cancellation. It's not capped. It tends to infinite as the two variables move to the same point. Okay. So now we can start with today's session number 8, with Monte Carlo simulation. Today we will understand the basics of the simulation. We will understand what is Monte Carlo simulation, how can we use this technique, and why this is very useful. We will learn how to select the probability density function, because we need probability density functions as input to the model. For the linear error propagation, we didn't really need a probability density function. We just needed a confidence interval that, of course, it implicitly has a probability density function, but we don't need to define it in particular. We just need the confidence interval, and we need to define the uncertainty in relative terms. We just need the value of the uncertainty, 5%, 10%, 50%, 100%. That's our input to apply the linear error propagation approach. That's what we need, this percentage uncertainty. When we move to simulation of Monte Carlo, that's not enough. We need to define the probability density function. So we will learn how to do that. We will see some good practice in selecting probability density functions. We will try to identify typical problems. What happens if we select something that it's not so appropriate? You may face problem of having negative values that are not positive, that are not realistic, for instance, for an emission factor, or having very long tails that are not really representing the variation of the inventory. So we will see a few cases and problems and typical situations that you should try to avoid. And we will deal a little with correlation, see how we can identify correlation, what correlation means, what's the implication of ignoring correlation, and what happens if we include the correlation into the model. So first, and just a very brief introduction of the Monte Carlo simulation, because the idea is not to go very detailed in the concepts of the Monte Carlo simulation itself, but it's important for you to understand where it comes from and what are the situations where Monte Carlo simulation works well and how to apply it. So Monte Carlo simulation, it's a numerical method. It's a numerical technique. It's non-deterministic, so it's random. It's a random technique. It's based on random science in probabilistic approach that simulates the behavior of a system, a random system, but the system is static. And what does it mean? It means that if we assume a probability density function for a parameter, that distribution is not modified during the time. It doesn't change with time. It's always the same. It's static. It doesn't change. So the average keeps the same. It's not moving up or down. The standard deviation is not moving, it's not increasing or decreasing. So we assume that the system behaves static as a static system. It doesn't change over time. If we want it to change over time, we have to update the probability density functions we are using to match the movement of the system. So that's one of the assumptions. The same, we had several assumptions for linear error propagation. We have some assumptions here for Monte Carlo simulation. And this is one, and it's the most strong, perhaps, assumption under the model. So we cannot apply Monte Carlo simulation if our system is changing in time. We have to apply it several times following the change if we want to do that. So the system, the technique by its own cannot deal with variations in time for the parameters. So whatever the process we are modeling, in particular, the Monte Carlo simulation was developed for random process because it's a random simulation technique that if you model random process, you, as an outcome, you will see a random output. So you will not see a number, you will see a probability density function as the outcome. However, although it's a random simulation technique, we can also apply it for the deterministic process, like calculating the GHG inventory. It's a deterministic value. We have activity data, we have emission factors, we have some other parameters. We calculate the emissions, and we have a value, the emissions of the inventory. So that's the deterministic process. However, we can apply simulation, the Monte Carlo simulation here, to simulate the random behavior of the variables in the sense of their random errors. So since we don't really know the value of the variables, and we know an interval where the value is expected to be contained with high confidence, 95% confidence, we can say that we can model randomly this lack of knowledge of the true value of each variable by assigning a probability density function to each of them. So it was, of course, came from Monte Carlo. It was developed for random games, a casino, and it's very quickly was adopted for deterministic processes for other cases. So in this case, we will be applying Monte Carlo simulation. Monte Carlo simulation technique is applicable to a very wide range of other activities. So it's not specific for GHG inventories at all. So you may use this technique to whatever other thing you would like to. So for instance, this technique can be used to calculate complex areas, figures, or optimization processes, or a lot of, in the financial industry, calculating the risk of a positive revenue in a business model. It has a lot of different applications. So I think you will be very useful once we learned how to apply it. So the basic, when we apply it to our national inventory systems, what we are doing without considering uncertainty is that we have our spreadsheets in general in Excel with the inventory calculation system. We have all the equations, and we input the data, the activity data, the emission factors. We input all the parameters we are using for every single source of emissions, and we calculate the results. We add all the emission sources, and we get the value of the result. So what does Monte Carlo simulation do? Well, basically the same. You calculate the emissions at several times. So imagine that you calculate your GHG emissions for your country. And imagine that you are not sure about some of the values you are using, and you ask a colleague to recalculate the GHG inventory. And this colleague does it and provides you with a result. And you compare your result with yours, with your colleagues. If your colleague made some different assumptions, the result will be different. Then you may reach another colleague and ask to recalculate the GHG inventory. And this other third colleague does it and arrives to another estimation of the GHG inventory. If you could be able to have enough colleagues to do this, like 1,000 times, if you had 1,000 colleagues doing the inventory on their own, completely independently, using the same information and the same knowledge and understanding and variability of the different data, you will end up with 1,000 values for the same GHG inventory in the same country in the same year. So you may be able to plot all these results, and you will probably see something very similar to a normal distribution with an average value and a standard deviation. That is what Monte Carlo does, but without needing 1,000 colleagues or 10,000 or 1,000,000 colleagues. You simulate the inventory and you recalculate the inventory several times, where each time the inventory is calculated assigning the input variables one value in particular randomly, but following its probability density function. So if we substitute the input to our GHG inventory, if we substitute the input, and instead of introducing a value for the fuel consumption or a value for the emission factor or a value for the number of cows or a value for the amount of propylene produced in the country, if we substitute those values for their probability density functions, we are able to run a simulation where we can calculate several times the number we want, 10 times, 100 times, 1,000 times, 10,000, 1,000,000 times. That's one of the variables we can control in the simulation, how many simulations we will do. So we recalculate the inventory a definite number of times, and we will obtain a lot of results, which we can plot on softwares used for Monte Carlo simulations. Already have this graphic designs built in, so it's very user-friendly. And you will obtain, as a result, a probability density function that considers the random variability of all the input variables we included and how this variability, depending on their range in each of the cases, impacts the result. So we will obtain a probability density function of the result. That is why this is a random simulation. The input values are random values, and the output is a random value because we don't have one single value. We have a lot of values, and we can have all the statistics on those output values, the mean, the median, the mode, the standard deviation, the standard error, the coefficients of whatever. So we can run all the statistics analysis on those inputs. That's the idea. And the good thing of Monte Carlo simulation, since we are able to include the probability density functions as the input parameters, we don't care if the uncertainty is large or small. So we don't have this restriction we had with linear error propagation. We don't care if the distribution are symmetric or not, because we include the distribution that fits our data. If it's asymmetric, we just include an asymmetric probability density function, and that's it. We don't care if values are correlated, or in reality, we can explicitly model any correlation between two variables. And we don't care if we have complex equations that are not multiplication or addition. If we have power, if we have sines, cosine, exponentials, logarithm, whatever equation we have, we don't care. We just put the equation, and the model will apply this equation with the random input we included as a probability density function. So most, or I would say all of the assumptions for the linear error propagations can be removed for the Monte Carlo simulation. I see the chat. Does it consider the variability in the emission factors also? Of course. If you model the variability of the emission factor, the simulation will take that into consideration. That's depending on the variables you define as the input. So you may probably start imagining the level of effort that this simulation may require, because we need to define the probability density function for the input parameters, and we may have thousands of input parameters in a national GHG inventory. So it's not realistic to define all the input parameters as probability density function, and that's why once again I will tell you the importance of the sensitivity analysis to identify the key parameters that we should include in the simulation. So what are the main steps for implementing a Monte Carlo simulation? There are a lot of commercial softwares that can be used for Monte Carlo simulation. Most of them are with charge. In general, you may have some free trial versions for 15 days, 30 days, something like that. But in most of the cases, they are all with charge. They are commercial softwares. There are a few cases where they are free of charge. They are open source. There are some macro in Excel, some Excels already available that you can find that have some macro built in. There are open source that you could apply, use. But independently of course, you could just build your own Excel with Monte Carlo simulation. It's a lot more demanding, and you don't have the very nice graphic interface. But you could apply this in Excel. We will see an example in the Excels you have. There is a tab that it's a comparison between linear error propagation and Monte Carlo. That tab, I created a simulation directly in Excel using some normal distributions and log normal distributions as formulas there. So we will review a little the Excel there, so you better understand how it works. But basically, what we need for Monte Carlo simulation is that we have to build the calculation model. You may already have it in most of the cases, because that would be the Excel you are using to calculate your national GHG inventories. So that's the calculation model. You go to each category, you select the approach you will use to calculate the emissions, the tier 1, tier 2, tier 3. You include the equations, and that's your calculation model, to which you would like to understand the uncertainty of the result. Then it's very important you identify the key variables. What are the variables that are really important to the calculations? The first selection in general is made based on the understanding of each category. You may ask the experts in each of the categories which ones are really important, which are the variables that are the driver of the emissions, which are the variables that an expert expects or knows that it's the most significant to that category. So you do the first selection of relevant key variables based on that. You may use this technique of sensitivity analysis. It is it needs some kind of demanding. Excel has some built-in function to do sensitivity analysis, but you can just, if you suspect a variable is important, is relevant, what you may just do is artificially change the variable a little in your inventory and see the impact of the result. That's called it's a very known technique. Don't remember the name now, but it's a very common technique, experimental perturbations or something like that, in which you on purpose introduce a perturbation in one of the variables, let's say 10%, and you see how the perturbation impacts the result. So that's the idea of sensitivity analysis. If you moved one variable 10%, if you change it 10%, and the result change more than 10%, that's a very important variable. If the result change 1%, that may not be a very important variable. So, of course, in general, the result will not change a lot if you just change one single parameter, unless this is a very important category, a big category, And if you change it a little, the impact will be high. But if it's just a small category, we will not see a result. But that's one of the first things you should do to try to identify which are the variables that are really important, and you will like to put resources, time to assign and better understand the behavior of those variables and assign probability density functions. The next step is precisely this. Establish the probability density function for each of the input variables you identify that are important, and defining the probability density functions means deciding which probability function to use, if it's a normal distribution, a log normal distribution, or whatever other function, and determine the parameters defining the probability density function. For instance, if you assume that would be most of the cases a normal distribution, you have to say to the model, this variable behaves as a normal distribution, and the normal distribution is determined by its mean and its standard deviation. So you have to assign the mean and you have to assign the standard deviation for that probability density function. The same happens with log normal distributions. There are other functions that require, like a triangular normal distribution requires the interval and the most likely value. So depending on the information you have and depending on your knowledge of the variable, you will assign the probability density function and you will determine the parameters that define it. So you may use, we will go through how to determine probability density functions and what are the parameters and the cases where we may select one or the other. But in general, you may have a lot of different type of probability density functions down there. It's not likely that we will use a lot of different probability density functions. In general, GAG inventories behave as normal distributions or some log normal. We may, in some cases, we may not have enough data to determine a normal or a log normal distribution, so we may approximate the behavior to a triangular, for instance, or something similar. But it's likely that if when you apply Monte Carlo simulation, you only use 3, 4, 5 at most probability density functions, not much, not more than that. So you define the probability density function, and then you run the simulation. You have to determine the number of simulations, how many times you want the simulation to recalculate the inventory. We will see how to determine this value, because it's quite important parameter of the simulation. And then you will obtain the probability density function of the result. You will actually obtain a histogram of the result from which you could extract the 95% confidence interval. So you will achieve something like that. That would be the result of your simulation. And from that set of data that you can visualize into this type of graphs, the histograms, you would be able to extract the mean value, the standard deviation of this set of data, the confidence interval for the 95% confidence interval, the lower limit and the upper limit, and derive the uncertainty from that. In this case, for instance, if we achieve to a situation where the set of data we have as an output yields an average value of 100 and a standard deviation of 15, and we assume that the confidence interval it's around 2 times the standard deviation each side, we may say that the uncertainty for the result would be 30%. Just in case, this would be 15, it's the standard deviation, multiplied in reality by 1.96. It's around 2. And we divide it by the mean value. So that gives us approximately 30% of variation in our GHG inventories when we consider the variation in all the input parameters we decided to simulate. So that's the idea of the Monte Carlo simulation. And that's how it works. So let's see how it looks in an example. This is just this is not in the Excel, it's just an example I included in the PowerPoint for you to understand how a commercial software may look like if you haven't used a Monte Carlo simulation software ever. You may not really see how it works. Most of the commercial software are add-ins that are built into an Excel, so you download the software. You open Excel, you open the software, and the software creates a new tab. In this case, this is one of the software I have more experienced is at risk. It creates a new tab in Excel. Creates a new tab in Excel, from which you can just click. You just click, and you see a lot of options related to the Monte Carlo simulation. So this is how it looks like, how a commercial software looks like in reality when you add it to Excel. So you have here some options like how to define the probability density function. You have the option to add the cells where the outputs you would like to simulate are. So in this case, if you want to simulate the result of the whole inventory, you will select that cell where the value is. You will select that cell and indicate the system, the model, the software, that this cell is the output you would like to simulate as an output. You may insert functions. You have options to assign correlations between different values. If you have a set of data, you have options to fit a distribution instead of you trying to do a statistical analysis and come up with a probability density functions and their values. You can just click here and select the data, and the software will automatically provide you with suggestions of probability density functions and their associated parameters. You can create just a probability density function. You can create several models. This is where you tell the system how many times you want to calculate the inventory, how many times you want to iterate and calculate. That's the parameter we will use here. I will go to a chat for a little. Is at risk due to software publicly available? You have to pay. You have to pay a license to use. You have to buy a license to use it. I think it has, or it had a trial version. You can request if you would like to test it, but you have to buy a license to use it. Can you walk us through the Monte Carlo in a software with an example? And it's a commercial software, okay. Is there any freeware that offer the same possibilities as risks? Yes, I will suggest or point you to some alternatives you may use. Yes, Argo. Thank you. Argo is an open source Excel add-in that I understand it's free of charge, so you may use it. Thank you, Jorge. Thank you very much. And there are, as I mentioned, there are several spreadsheets, Excels, that contains macros already included that you can just download the Excel and use the macros that are included there. But Argo is a very nice software. It's very similar. It has not the same power or graphic design as at Risk, but it's a very good alternative. So in here, going back here to the presentation, this is where we tell the system how many iterations we would like to do. So in that case, what's the implication here? If we run very little simulations, we may have not enough data so as to really understand the behavior, the random behavior of the result. So the idea is to increase the number of iterations until we see that the probability density function we are seeing as an output, or the histogram, more or less stays stable. If we start increasing the iteration number and we see that the average and the standard deviation more or less start to converge to some values, then we realize and know that we are with enough high number of iterations so as to have reliable values. In general, 1,000 simulation, 1,000 iterations, it's good enough. There may be cases that you may need less than that, and there are other cases that you may need more iterations. But the first start, the selection, and in fact, 1,000 is one of the default values for most of the softwares. So that it may be the case, it happened to me, just as anecdote, sometimes depending on the size of the spreadsheet, the complexity, and the computer you are using, it may take some time if you put a lot of iterations there. So you may start with your computer running for several minutes or even hours, depending on how your model in Excel was built, was created. So I suggest you start with a small number of iterations, around perhaps 100 or 500, and see how it works. And if you see it's fast and you have no problems, you may start increasing from that to 1,000, 2,000, 5,000, 10,000, and you will see when you've reached enough iterations. I see a few comments in the chat. Is there any guides for choosing a specific probability density function for a variable when we have only the default and range of the variables? Yes, we will see this during this session, how to select probability density function based on the data we have. Can you use Solver add-in Excel for Monte Carlo simulation? I'm not sure what you mean with Solver, but these commercial softwares are add-ins. I guess Excel has some built-in function called Solver. I'm not sure if that's the issue. That may depend on the version of Excel you have. If that happens, I really don't know, but if that happens, that your version of Excel has some solver that runs Monte Carlo simulation, you probably are good to use it. I see. Thanks, Armando, for sharing the link for Argo. That's the Busal and the GitHub. Yes, that's a free source, open source website. How we can add risk? Not sure what you mean. How can we add? If you already have it, you just have to open the software and Excel. If you don't have the commercial software, you have to download it, a free trial version for limited time, 15 days or something like that, or you have to pay for the license. At risk, just to make it clear, at risk is the one I used and I have more experience, but there are a lot of different commercial software that can be used. So if you are interested in acquiring commercial software, just do a research of the available software there and ask for the quotation, how much does it cost and everything like that, because that there are a lot of alternatives. Let's see a few answers to Solver. Yeah, I know Solver works for optimization process or iterative process finding some target results, something like that. I'm not sure if it works for Monte Carlo simulation. Okay, so if you see here, I will open the laser pointer. If we see here in this cell that is here, I'm highlighting, in our GAG inventory calculation, this cell will have a value 0.01, for instance. This is the emission factor for nitrous oxide emissions in fertilizers used. And we have the range here. But if you see in this case that it's built in as a Monte Carlo simulation, you will see that this cell is really not containing a value anymore. Now, what this cell has is a probability density function. So I changed the value 0.01 from this cell that I've used to calculate the emissions in the GAG inventory. I removed the value and I've included a formula that it's representing a probability density function. In this case, it's a log normal distribution with a mean value of 0.01 and a standard deviation of 0.006. That's the parameters defining the log normal distribution. So this cell is not a number anymore. Now this cell is a random variable with random variability represented by a log normal distributions. So this is what it's really in the cell. Now we model this variable. We identify this variable as a key variable. So we model this variable as a log normal distribution. So every time we run the simulation, this cell will get a different number, will not be 0.01 anymore. The cell will get different numbers every time we iterate, and the numbers will vary in this interval and will be assigned based on the probability of each of the values in this interval. So from this range down here, the values near this central portion will be selected more frequently, randomly, but more frequently, because they are more likely to happen than the values here or here in the tails. So you may expect these values that are around 0.03. You do not expect to have a lot of cases where these values appear in the simulation, but there will be some of the cases where those values appear. So this variable will now change constantly every time. In this case, 1,000 values will be assigned here following this probability density function, and the calculation of the inventory will take into consideration every single of these 1,000 cases. And that's repeated, that happens simultaneously with all the variables that we've simulated, that we introduce a probability density functions. Each of these variables will simultaneously yield some specific value depending on their probability density function. And this will be translated into the result of the emissions. And after doing that 1,000 times, as we selected here, we will have the result of 1,000 calculations of emission reductions, of emissions in the GHG inventory. So that's how it works. That's how it works. I will just move now to the Excel to show how this Excel was implemented applying Monte Carlo simulation. I will stop sharing the screen. And I will share quite a long Excel. I hope you can see my screen. You can, of course, see your own Excel file.
Yeah, yes, we can see your screen, but it's a bit, can you make it a bit wider?
Yes, I can zoom in a little. Okay, so just a brief description. The idea is not to fully explain each cell of this spreadsheet, but just for you to give you an overview of how this was created. How I included all the values. This spreadsheet contains approach 1 and approach 2, linear error propagation, and Monte Carlo simulation. Both approaches are included here. But also comparing the cases where we have correlation and we do not model the correlation, and what happened when we model correlation. For this time, just forget about this correlation or not correlation. We will see that in a few slides today. I just would like you to focus on the Monte Carlo simulations. So this case was created for energy sector, where we have fuel consumption. We have the national statistics of the amount of gas oil consumed in the country. And we have the statistics of how much of it was consumed in the different sectors. So if we were calculating the reference approach of the GHG inventories, we would just use the amount of gas oil consumed, and that's it. For the sectoral approach, we need to discriminate this amount of gas oil into the relevant sector, how much was consumed in transportation sector, in the industrial sector, in commercial and residential. So let's assume we have all the statistics that discriminate the amount of gas oil consumed in each of the sectors. And we know, we investigated and we arrived to a conclusion that this data of the amount of gas oil consumed in each of the sector has an uncertainty of 5%. So that's what we've been able to collect for the energy agency in our countries. We are using the emission factor of the gas oil from IPCC. So we have the default value, the lower and the upper limit, and we are able to calculate the uncertainty of those figures. So what we will do is just to run the simulation. Let's just focus here. So how can we run a Monte Carlo simulation here? Well, I said that we need to model the variables. We need to assign probability density function to the variables we want to model. So the variables here are the energy consumption in transport, the energy consumption in industrial sector, the energy consumption in commercial and in residential. Those are the input variables we are using, and we are applying the default emission factor. So all these are the variables, are the input parameters we are applying in the formula. So let's simulate, and let's assume in this case that this consumption behaves as a normal distribution. So what I just did was manually create the simulation of, let me go to the bottom of the spreadsheet, a simulation of 500 cases. So I've recalculated each of the variables 500 times following a normal distribution. I'm not sure I don't know if you can see the formula there. But what I just did was to assign this cell. I tell this cell that this is not a number, that this is a normal distribution. I don't know if you can see here. I've included this is a normal distribution. And I would like this cell to have a value according to a normal distribution that has a mean value based on the amount of gas oil consumed in the country applied to a 70% of the gas oil is consumed in the country. So this is the 63,850 total gas oil multiplied by 70%. That's the fuel consumption in transport sector. That's the average value of the standard distribution. And here I've included the standard deviation of the normal distribution. This is the standard deviation that's applicable to an uncertainty of 5%. So if you remember, and this is very important because it's a very common mistake when applying Monte Carlo simulation, we've been dealing with uncertainties and pay special attention to this, what I'm going to say. we've been saying that uncertainty is described as the 95% confidence interval. So half of the interval, half of the 95% confidence interval in relative terms, that's what we've been using to define uncertainty. That's what we need when we use linear error propagation technique. But for Monte Carlo simulation, we need to define the probability density function. So what we really need, it's not this half interval of the 95% confidence interval. What we need is the standard deviation. So if we assume a normal distribution, the half width of the 95% confidence interval will be around 2 times the standard deviation. So that's why you see here that I divided the uncertainty by 2, because that's more or less in reality, I should have divided it by 1.96, which is the statistic for the distribution, but it's really a negligible difference. So it's okay if you just use 2 for these cases. So that's why you could see this 2. So the standard deviation is not 5% of the mean, it's half of this. It's 2.5% of the mean. That's the standard deviation. That's the value we need to use here in the simulation technique. So this is the multiplication. It's just because I'm multiplying the total consumption by 70%. So in this way, if I just extend this cell, you see how it recalculates every time I double click here. It recalculates all the 500 values here. It recalculates all of them following a normal distribution with a value, an average value of 63.850 and a standard deviation of half this uncertainty, 2.5% of the mean. And you can see here, I calculated the average of this result, and you can see it's very, very close to the value we are using. And every time I recalculate it, it changes. Of course, it changes because it's random behavior. And you can see here the standard deviation that we achieved. And we can see here the 2 times the coefficient of variations, 2 times the standard deviation divided the mean, that it's around 5%. That's the input that we included in our model. I will go back to the chat just for a few minutes, see if there's something to clarify.
Diego, there are some questions in Spanish. Maybe we can try to respond to them. Yeah.
Mm-hmm. Yes, I see a question about what happened when you have several calculation tools that are quite extensive. What's the best practice there? So, for instance, if I have a tool for forestry plants and another for wood products or collected wood, you have the 2 of them are quite extensive, I imagine. Well, the good thing with Monte Carlo is that you can apply it independently. You can apply it for one tool and not for the other. for the two of them, or for a portion of the tool you are using. So, because the interesting thing is that if you run the Monte Carlo simulation into one of these tools you mentioned you have, you will be able to arrive to both a probability density function of the result, which you could just use as input into another spreadsheet and simulate this variable with that probability density function and those parameters, the mean and the average, the mean and the standard deviation. And those will come from a separate simulation you've done. So that's something you can do. It's very flexible in that sense. Or you can just translate that probability density function into a confidence interval, into an uncertainty value that you can then apply with linear error propagation, for instance. That's a combined approach we will see tomorrow. So you can select according to the effort required, according to the information you have, if you would like to apply a Monte Carlo simulation to all the categories altogether, separate some part of it, or how you want to deal with that. What's the value in cell F19, F20? Okay, column F, that's the random value. It's just a function, it's random. This is just to tell the probability density function, in this case, the normal distribution, to assign a value based on this random number. This random number goes from 0 to 1. So depending on the value, the probability density function, the normal distribution, will assign a value comprising, in this case, the value that represents the 87% that contains 87.2% of the values. 87 to the left, the remaining to the right. That point within the probability density function, that point within the normal distribution will be the selected value. This would be the value that represents 41%. This 39. This is a very limited. This is one of the extreme values. It's 99.6. So this random number is used to assign the probability of having a determined value for this normal distribution. In this case, so that's just how I built the model. You could, instead of having it separate, you could just build it in here. So that's the thing. What's the aleatory number in the formula you're actually showing? How it's defined? Well, it's the same. I just explained. Could you please use a pointer or marker in the sheet? That would be okay. Okay, thanks for the suggestion. I will use a pointer so you can easily see where I'm referring to. Is the uncertainty of the sample transfer assumed 2%, the same as that of gasoil? The assumption for the gasoil is 2%. The assumption for the spectral consumption is 5%. It's the value. If I can. The value here is 5% is the uncertainty for the sectoral disaggregation. After doing simulation for different strings, and then we can combine the uncertainties of all the strings. 2 sigmas of mu indicates, okay, that's here, this cell. 2 sigmas of mu indicates the confidence interval, half-width confidence interval, the uncertainty in particular. So you can see here, these are all very similar to the 5% data we've introduced as the variability, the random variability, the uncertainty for the input data. So going back to the Excel, we have here, so we simulated the fuel consumption, transport, and we did the same for industrial sector, the same for commercial sector, same for residential sector, and here we just added, I'm not seeing an option here to use a pointer in the Excel. Sorry for that. I'll try to highlight the cells I'm referring to. So here I just calculated the total values, just the sum of all of them. And here you can see that I just calculated the emissions. And when I calculated the emissions, what I did was multiply the simulated variable, simulated value for the fuel consumption in transport, and I multiply it by not the emission factor, not the value of the emission factor, but a simulated value also considering the variability as a normal distribution. You could see here in this cell here, that I will just highlight. This cell, the formula here contains the simulated value, G19, that's the consumption, fuel consumption in transport, one of the simulated values, and I'm multiplying this by the emission factor, but in a form of another normal distribution that again is built based on a random number. Here, the column L, here, the random number, here, the mean value of the emission factor, that it's cell C17, it's 74.2 here, 74.2, that's the average value for the emission factor. And then I included the standard deviation associated to that value, which is 2% of the mean value, that's the uncertainty, and I divided by 2 to convert the half-width interval of 95% into the standard deviation. So this cell, again, it changes every time I press enter. So this changed this cell, and I did the same with industrial, commercial, and residential. So I did the same for every of the sectors consuming electricity. And I just repeated these calculations 500 times. So I simulated the behavior of the inventory, of the calculation of the emissions 500 times for each of these sectors consuming gas oil in this example, and I've recalculated the emissions associated to the gas oil consumption in each of the sector 500 times. So in the end, what I have was 500 values of the emissions associated to the gas oil consumption in each of the sectors. So now what I can do is just get the average value of this result. I can get the standard deviation of this result, and I can calculate the coefficient of variation, or the uncertainty in reality, 2 times the standard deviation divided by the mean. And we see that according to the simulation we've created here, we simulated the activity data as normal distributions. We simulated the emission factors. In this case, there is only one, as a normal distribution. And as a result of that, we obtain an uncertainty of the associated emissions that it's 4.6%. You can see that it changes every time, but it's always around similar values. That means that the number of iterations I've included, 500, it's enough. So we don't see huge variations here. It's always around 5%, more or less. So that's Monte Carlo simulation. For a very small portion of the inventory, just fuel consumption for 4 sectors and just one fuel and just one gas just for CO2. But this is the essence of what we are doing, and we can repeat this, of course, if we start increasing the number of categories, the number of fuels, the number of gases we are calculating. The spreadsheets start to reach a complexity level and a volume that it's not really manageable. So that's why, in general, you use a commercial software to perform the simulations. But if you would like to start simulating or applying Monte Carlo simulation, it's a good practice. You just apply it to one category just to learn and make your own experience on how it works. So you can start build from that small example, and you can grow the examples as you need, or you can apply it to key categories in particular, so to get better estimates of the results. I will go back again to the chat to see if I'm missing some questions. Each time I'm checking the mu value for activity data, every value of the column G to Q changes. Yes, of course, because it's assigning random values. In what general cases are the other recommended probability density functions used? We will see when we can use, just in a few slides, when we can use one distribution or the other. The uncertainty of total is 4.2, but in the cell D6, the uncertainty is 2%. Why they differ? Well, 2% is the uncertainty of the activity data only. It's not the uncertainty of the result. It's the uncertainty of the activity data, but aggregated the whole gas oil consumption in the country, not the uncertainty for the sectoral consumption. So it's the uncertainty of the activity data. How to do Monte Carlo simulation for a category which has several multiplicative factors, for example, crop residue burning, where we have area burned, fuel available, moisture content, etc. It's the same. You just simulate each of the multiplicative terms, you multiply, you calculate the result, and that's it. It's exactly the same. That's the good thing of Monte Carlo. It's not depending on the equations you are using. You have just to model the input data do the calculation and obtain the result. You don't have to worry by the type of calculations. The only issue there to perhaps to consider that when we have multiplicative several values that are multiplied all together, the result will tend to be asymmetric. That's the essence of log normal distribution. So in a category, even if you include normal distributions for the input values, when you multiply all together, the resulting probability density function will start to make asymmetric, and the more values you are multiplying, the more asymmetric it gets. That's the nature of that process. So for those cases, you will end up with an asymmetric result, so an asymmetric uncertainty, which if you want to include it and keep a Monte Carlo simulation, you will have no problem. But if you are planning to use these values into a linear error propagation, you will have to make some assumptions to assign a symmetric uncertainty. Could you please explain the formula again? This norm involves the formula for the normal I will do it just in a few seconds. Let me check the rest of the comment. How to generate the random variables and how is uncertainty value 2% at D6 obtained. That's not obtained value. That's an input data. That's the result of what we research. In reality, you will go to the national agency providing the statistics and you will ask what's the uncertainty associated. And if you are lucky, you will get a result. And if you don't, you may try to find some similar cases or go and use the references and the guidelines in IPCC guidelines related to the uncertainties that could be expected from national statistics. So the formula, I will explain the formula again. We have 30 minutes left, so I will explain the formula just one more time. But you can play around on your own on how to use the formula. But let me just create one formula here. Imagine you want to define a normal distribution with an average value of, I don't know, 50 and a standard deviation of, I don't know, 20. So how do I build this formula? I will build it here. So I will include norm inverse. Let me just copy here. Oh. Let's put it directly. I will try to find a formula associated to a normal distribution. But since with a normal distribution, you may know the value and would like to understand the probability of that value to happen. That's the normal distribution formula. Or you may have the probability and would like to see the value associated to that. And that's the one we want, and that's the inverse of the normal distribution. So I want to tell this cell to behave as a normal distribution, and if I include a probability here, and I include it as a random number, I write random, that will give random numbers from 0 to 1. So I am assigning the probability from 0 to 100% for values. for a normal distribution with an average of 15 and a standard deviation of 20. And that's all. This cell will now show one case for the normal distribution with these parameters, depending on the random figure. So in this case, I will just reduce the decimals to make it easy to follow. And let me just fix these cells so I can extend this. So if I extend this formula, I will do it until there. What I will have is just a simulation of this parameter. I am simulating here a parameter, a normal that is defined by a normal distribution with an average of 50 and a standard deviation of 20. And I have in here 3, 4, 5, 6, 7, 8 values, 8 dumplings, 8 simulations for this variable. You can see the average, it's in this case 46.3. So it's quite, this is how we see the average. If the number of iterations were enough, the average of this should be similar to 50. So we are having 46 for this case. So if I add and I run and I extend this cell like 1,000 times, I should get an average value very similar to 50 and a standard deviation very similar to 20. That's how this formula works. You see a case there where asking what's the difference between the uncertainty correlated and uncertainty not correlated. Okay, we will see there in a few slides if we have time. I hope so. But it's basically, in one case, I am assuming that the values are independent, and in the other case, I model explicitly a dependency between the two variables. But I will just go back to this when we see the correlation issue. Do the syntactic commands remain the same across the softwares? In this case, for Excel, depending on the version of Excel and the language, of course, they may vary. In the commercial softwares, the syntaxes are different. They are similar, but not exactly the same. But they are quite similar. What you should be careful, in particular for log normal distributions, you should be careful on how the variables are defined, because log normal distributions may be defined in terms of their own mean and standard deviation, or the mean and the standard deviations associated to the normal distribution of the log normal. I'm not sure if you followed me, but you have to, I suggest you, if you are using our commercial software, to go to the help menu and read how each of the variables, each of the probability density functions are defined for that particular software in particular. So let's move back to the presentation. I will stop sharing the screen here and I will share again. I will go back to the presentation. You should be able now to see the presentation again.
Yes.
So let's go quickly through. Now we understand what simulation, what Monte Carlo simulation is. Talk a little about how to assign, how to select the probability density functions. And what are the most common probability density functions you will probably use? So first, you have to consider the variable, the domain, if it can take negative values or not, the range, if the range is small, probably a normal distribution will fit very good. However, if the range is broad, you may start to assess if you need a normal or a log normal or some other distribution, even if the variable is not symmetric. If the range is small, you may still apply a normal distribution and you will get pretty fairly good results. The shape, if it's symmetric or not, the underlying process, if the variable you are using is coming from, as I mentioned, from a multiplicative process, and you are just getting the result of the value, it probably may be good to select a log normal distribution. If it's a result of the addition of several other values, it will probably behave as a normal distribution. So knowing the variable is the first thing you should try to understand. So what are the most common probability density functions you may use, and when you may use one or the other? The most basic and the most basic probability density function is just to assign uniform probability to any variable. You may not use this very much. This is a case you just need to define the variable. You just need the minimum and the maximum. You just define the range, and that's it. Every single value within the range you define can be selected with the same probability. That's uniform probability density function. The problem with this is that you don't have a most likely value, so the uncertainty in the results will be wider, will be higher. And you may use this in cases where you really have very little information about one variable. So if you only have the range where the variable is, and that's all the information you have, you may use this function. The good practice or the suggestion is try not to, and instead of using this value, this function, try to investigate a little deeper into the variable to see if at least you can have some sense of where the most likely value are. So in that case, you may be able to use a triangular distribution. If you know the range and you know the most likely value, you can apply, and if that's the only information you have, you may apply a triangular distribution. And you define it by a mean value, a maximum value, and the most likely or the mean or wherever you want this peak to be, noting that it's good, very flexible in the sense that you may use a triangular distribution for a symmetric distribution or asymmetric. If you just say that the mean value is closer to the left-hand side or closer to the right-hand side, you may include asymmetry into the triangular. So it's quite intuitive to use. It's very useful, and it gives pretty good results without much effort. However, if you know that in reality the probability density function is, or the variable is behaving as a normal distribution, you should probably apply a normal distribution and try to derive the mean and the standard deviation. I see a few comments in the chat. The value at the 62%, it's related to the Excel. You have said it's obtained from the stakeholder. How's to have this value? What to do? They give me the total consumption in liters. To collecting data for uncertainty, you have to go to the national statistics, to the agencies associated to that statistics, or apply some statistics techniques, as we saw on Monday and Tuesday and part of yesterday, Wednesday. That's how we collect the information for the input data uncertainty. We may follow up with you offline, just not to diverge from the topic today, that it's propagation with Monte Carlo. How to define symmetric distribution for linear error propagation if we get asymmetric distribution after multiplication in Monte Carlo simulation. Well, that's one of the problems with linear error propagation. You need to define a symmetric interval with, and if you have asymmetric results, you have to put to apply some assumptions. You may use the higher value, you may use some average, you can apply some techniques that are described in the IPCC guidelines. In the chapters related to linear error propagation, there is a portion that describes how to deal with asymmetric uncertainties. You can apply it. In my experience, what works best is using something in between the lower limit and the upper limit. Using either of them, it's not really good. Using something in between gives pretty fair results. What distribution do you recommend for fuels emission factor in the form of national inventories, which are not symmetric? In general, the emission factors of fuels, for most of the fuels, tend to have low uncertainty. So you may assign, even if you see some asymmetry, you can still use a normal distribution and you will have quite good results. If the fuel you are trying to model, it's coal or biomass or some other fuel that have wider intervals and maybe more asymmetric, in that case, you may apply a log normal distribution or some distribution that allows you to model the asymmetry properly, trying to match the confidence interval that you may find in IPCC guidelines. If an emission factor is published with absolutely no information on uncertainty, nor confidence interval, nor standard deviation, can a normal distribution be assumed? In general, yes. If it's depends on the emission factor. If it's related to fuel consumption, we are pretty confident that a normal distribution may work well. If it's an emission factor for any other category, you may need to be more careful because it may be more asymmetric, like emission factor for N2O, for nitrous oxide emissions, for fertilizer, soil, things like that, tends to be very, very, very asymmetric. So in that case, you have to go to the basis and try to better understand the parameter you are trying to simulate so as to select the proper probability density function. What you would suggest for fugitive emissions that in general are more uncertain, the intervals are wider, and maybe in general, in my experience at least, they are asymmetric. So perhaps a log normal distribution, or if you let me move a few slides more, I will show you a few other alternatives than log normal that could be helpful. So normal distribution, I will not spend too much here because I guess we all know normal distributions quite well. But it's the most of the variables we will select for modeling will probably be normal distributions. So you just need the mean and the standard deviation. And one very good thing for this is that if we only know the confidence interval for instance, in the IPCT guidelines, and we know it behaves as a normal distribution, we can just easily derive the standard deviation as we just did, as half width of the 95% confidence interval divided by 2. Because if you move from the average 2 times, 2 standard deviations to the left, 2 standard deviations to the right, you will have this 95 confidence interval. So if you only have information of the confidence interval and the mean value, and you know the variable is normally distributed, you can easily identify the mean and the standard deviation so as to model it properly. Then we have the log normal distribution, which is fully related to the normal. If you have a log normal distribution and you change the scale and you plot the figures, the numbers in a logarithmic scale, you will see a normal distribution. That's the definition of the log normal distribution. And again, the parameters defining this are the mean and the standard deviation. It's good for emission factors in general because log normal distributions cannot be negative, and that happens with emission factors. So it's good representation, but sometimes the lower and the upper limit do not match properly if we have some data for the intervals. So for those cases, we may use other alternatives. One of these are gamma, the gamma distribution. It's a very flexible one. It's defined by 2 parameters. One parameters that define the shape, if it's symmetric or asymmetric, and the other parameters determines the scale of the distribution. So if you may calibrate these 2 parameters to match whatever data you have or to match the confidence interval and mean value you have. So it's very flexible in that sense. The beta PERT is another very flexible probability density function that you may use to match some cases that are not fully matching a normal or a log normal. If you're finding difficulties in trying to match the mean, the lower and the upper limit of the confidence interval, you can try using a beta PERT, which is very flexible. The good thing with this is it's very intuitive because it requires the same data as a triangular distribution. You just need the minimum, the maximum, and the mean value. And so if you have the confidence interval, you apply the minimum, you apply the maximum, and you put the mean value where your point of estimate is, the most likely value, and you will have a bell-shaped distribution, but with data that is very easy to understand, and it's similar to a triangular. So that's a very good alternative to match those cases. I mean, if you know a variable is normally distributed, or it's very likely that it's normally distributed, you just will select a normal distribution. And if you know that the variable is log normal, you will select log normal. But for those cases where they don't seem to fit well in a log normal, it's some skew, but not so long tails or some things like that, and you are having hard times to match a probability density function to the data, you may use this gamma or beta PERT as alternatives, and it will be quite easy to match the data you have. So a few good practice guidance for this. Just remember, don't be so creative in selecting probability density function. In general, you would use just 2, 3, 4. Don't get very creative in selective weird probability density function, but because probably they are not the real representation of the variability you are trying to model. base your selection on the knowledge of the variable. And depending on what you know about the probability density function, if you have no idea, you may just assume a normal distribution. In most of the cases, that guess would be appropriate. So that's no idea at all. Normal distribution may work well. There are some cases that you realize that it doesn't work, so after you may change it, but you may start with a normal distribution just to see what happens. If the variable must be non-negative, be careful if you assume a normal distribution and the standard deviation is large, because if that happens, it may happen that you end up the portion of the log of the normal distribution in the negative side, providing negative values, which are biasing the results you are getting, because that's not possible. If you are using an emission factor and the emission factor, the least value would be 0, and you apply a normal distribution that it's very wide, you may have a portion in the negative part, so be careful with those cases. An alternative to that is that you may truncate, you can cut the negative part of the normal distribution and keep the positive values. That could be an option. The problem with that is that you are changing the relative probabilities of the remaining portion of the normal distribution. So that's not the good practice. If you see that happens, it's better if you just abandon the normal distribution and apply another one that you can make asymmetric, or you can model properly, a log normal, a variable, a gamma, a beta paired, or other functions. If you use expert judgment, in general, a normal distribution may fit well, or a log normal if you see the result of the expert judgment is asymmetric. If you only know the interval, you may assume an uniform probability density function. Again, better you just try to investigate a little more about that variable and assign a triangular or other probability density function. And if you see that the data, if the probability density function you are using, it doesn't seem to fit, but you're quite confident that the probability density function is correct, the problem probably is the data you are using, that it's not representative, or that it has some bias, that it's not matching what it should be. So, some other alternatives to use goodness of fit test to select the functions. Be careful with the extremes. Some distributions have very different probability in the extremes, which may have a huge impact in the result. So basically, again, go to the basic, go to the knowledge and understanding of the variable you are trying to model, and use your best judgment to select the probability density function. Just have 5 minutes more. I will go just quickly through the issue of correlation when we have correlated values, and just to make it clear what correlation means and what's the implication into the calculation of the uncertainty. If there are correlation and we do not model that correlation, two things may happen. If the correlation is negative, meaning that if one variable goes up, the other variable goes down, that type of negative correlation tends to reduce the uncertainty in reality. So if we do not model the correlation, we will be overestimating the uncertainty of the result. And the opposite happens when we have positive correlation. In general, if there are positive correlations and we do not model it, we are underestimating the uncertainty. So these are just to make it clear, we all understand what correlation means. Correlation means that two variables move similarly, are linked one to the other. A correlation coefficient of 1, highly correlated, low correlation, or cannot be correlated at all. So these are just a few examples to show how correlation looks if we plot two variables, we may see these type of things and identify if we see correlation or not. Just for you to understand that correlation, it's not always linear. We may find, it's not so common, but there are some cases where we may find non-linear correlation. That's very common, for instance, in energy. In general, emission factor, net calorific value, fuel consumption, they may be correlated. If we have information of the fuel consumption in energy units, and we apply an emission factor that by default includes the net calorific value, we are having data that's not really independent. So we need to be careful on this type of things. But do we always need to care about correlation? Well, that's not always important. And we will see two parameters to understand if we have to worry about correlation or not. The first one is the correlation degree, and the other one is the impact to the overall uncertainty. And in doing that, we have the combination of the two variables, and we have four situations. A situation where the dependency, if we have no dependency at all, that's great. We can continue without worrying. But if we see correlation, if the correlation is weak and the impact of those variables into the total uncertainty is low, we don't have to worry at all. That's the best case. Then we may have two cases where either the dependency is weak, but the sensitivity of the variable is high, or the dependency is strong, but the importance of that variable is not high to the total uncertainty. For those cases, we don't have to worry much again, because either the dependency is weak or the importance of the variable is not too high. So the case where we should worry about when we are talking about correlation is the cases where the correlation is strong and the variables have an important impact into the results. So for those cases, we will try to address correlation. And here we are just on time, but you will have some bullet points to read on your own. We can go over them tomorrow to see some strategies to deal with correlation when it's important and when the variables are important to the result. There are some strategies to deal with these correlation situations. So that's all from my side for today. Thank you very much again for staying with me, listening to me. And I hope you find today's session useful. And back to you, Saben.
Yeah, thank you, Diego. I think now we know how Monte Carlo simulation works, how to select the probability density functions to describe the input data, including activity data, emission factors, and parameters, how to do the simulation, and also describe the outputs. We invite you to practice, because without practice, it's difficult to see all the aspects. So practice and get back to us if you have any questions, any challenges, and we try to help you. It's not that difficult. It may be time consuming, but once we build the system, the next steps are much easier. So we encourage you to practice, and to practice. Tomorrow will be the last day of the webinar, and we will see how approach 1 and approach 2 can be used together to combine uncertainty. We'll also see how uncertainty data can be integrated into key category analysis to prioritize the use of resources, and also the application of, and also we'll see how to derive uncertainty associated with the use of proxy splicing techniques and expert judgment to fill data gap. So we still have good session for tomorrow, and we invite you again to join the webinar at the same time using the same link. Diego, once again, thank you. I also thank the colleague from the Secretariat and people working on the interpretation. Thank you all for your participation, and we continue tomorrow. Thank you and bye-bye.